Welcome everyone. This is fourth video in graph theory series. I already have uploaded 3 videos, and for your convenience I am going to put those videos in the comment section as a pinned comment, so that in case if you are coming across this channel for the first time, you can watch them in the sequential order. And preferably you should also subscribe the channel to get good quality video content, because here we are uploading the very comprehensive content, so that all the topics of discrete mathematics is covered, and I already have created different playlist for that. So let's start. In this video I am going to talk about connectivity. So in connectivity we will understand that what is path and simple path, and another set of terminology that is used by some different authors like walk, trail and path. We will talk about what is cut set, cut vertices, cut edges, right? And we will be using the idea of connectivity to decide whether a given pair of graphs are isomorphic or not. So first of all, let us understand this thing, connectivity. So here we are going to talk about two terms. One is path and another is simple path, right? So to understand this, when I say what is path, a path is a sequence of edges that begins at a vertex of a graph and travels along the edges of the graph, always connecting pairs of adjacent vertices. A path of length n, this I am highlighting, a path of length n contains n edges. The path is a circuit if it begins and ends at the same vertex and has length greater than 0. Another part is that a path or circuit is simple, and that is something that we have to separate if it does not contain the same edge more than once. So it means what? Let us understand it through this example. So suppose I move from one vertex to another vertex in this graph. So let us start. Suppose I move from A to B, like I am putting arrows so that you understand that how the movement is taking place. And suppose I move from A to B, and then suppose say B to E. So B to E like this, and then E to F. Then I move from E to F, and then F to E. So I move from F to E, not F to E, this is F to C, sorry. So F to C, and then C to suppose I say D, right? And D to A. So D to A. So now I'm stopping here, right? So I started at A, I moved from A to B, so this is the first edge that I traveled. Then I moved from B to E, so this is the second edge. Then E to F, this is the third edge. Then F to C, this is the fourth edge. C to D, so this is the fifth edge. And D to A, so this is the sixth edge. So what is the length of this path? The length of the path here is equal to 6, right? And suppose I just consider the path from up to suppose D only. Let me write another example so that you don't miss. And before that, let me remove all these arrows here. So let us move through another path. So suppose I move from A to B, right? And this is the first edge that I covered. And then suppose I move from B to F. So this is the second edge I covered. Then F to E. So I covered it third edge covered. And E to B. So I covered the fourth edge, E to B, right? So we started at A. So one edge, two edge, three edge, four edge. So this is a path of length 4, right? Length is equal to 4, right? Suppose we take another example, and in this example let me start at E, right? So why should we always start at A only? So I start at E, I move from E to B, right? And then I move from B to F, and move from B to F, and again I move from F to E. So I move from F to E, and E to B again. I repeated this edge, E to B again. So I am drawing two arrows so that it signifies that I have moved across this twice. And suppose I move from B to C, so again B to C. So you notice that what I have done, I started at E, went to B, so one edge, then B to F, second edge, then F to E, third edge, E to B again, fourth edge, and B to C, fifth edge. So the length of the path length is equal to 5 here. And in the process you noted that I have repeated this edge more than once. So when we talk about path, there is no such restriction that an edge may be repeated, it may not be repeated. So there is no restriction, you can move through one edge any number of times. But when I talk about a simple path, in the simple path we are not allowed to repeat the edges. So when I say that if I repeat the edge, that path will not be a simple path. So let us take one example of a simple path, that I start at suppose D, and from D I move to E, and then E to F, and then F to B. So here I have moved from D to E, E to F, and F to B. So this is a simple path because no edge has been repeated, and the length of the path, simple path of length equal to 3, right? Now let us talk about another example to understand the meaning of circuit. So suppose I start at D, move from D to E, right, and then I go back to go to B, so I moved from E to B, and then B to A, sorry, so B to A, and finally I come back to D, so A to D. So did you notice what happened? I started at D, went to E, then B, and then A, and then came back to D. So what I did, I went back to the same vertex where I started. So what we have got? We have got a circuit, and this is a simple circuit of length 4 because here also no edge has been repeated. So the idea is, let me conclude this discussion, that if any edge is not repeated, then the path is simple path. If any edge is not repeated and if it is a circuit, then it is a simple circuit. If the edges are repeated, then it is just called a path. But before we move to the next idea, we should also understand some different terminology used by some different authors. So some author use the terminology walk, trail, path, and circuit. See, let me tell you one thing in the beginning here, that in our discussion we will be using the same term like path and simple path. I won't be using this terminology. This I am just talking so that you also be aware about these notations. Okay. So let us first talk about walk. So when we say walk is a just random movement, right? A walk is a sequence of vertices and edges of a graph. If we traverse a graph, then we walk. Vertices and edges both can be repeated. See, when I was talking about the previous idea, the path and simple path, I was not concerned about whether a particular vertex is repeated or not. What I was concerned about, that whether a particular edge is repeated or not. But here we are also concerned about that, what about the vertices. So to understand that, let us take this example. Suppose I move from A to B, and then B to C, and then C to F, and then F to E, and E to B, and again B to C, C to F. So I am just moving it. Here the vertex B has also been repeated, and this edge BC has also been repeated. So this is just a walk. In walk we just move random, like I start at any point and randomly move without being concerned about whether a particular vertex or any number of vertices have been repeated or any number of edges has been have been repeated or not. So all those things will be considered as a path. Means path is a very general term. We do not restrict any movement. But when we talk about trail, in the trail we are allowed to repeat the vertex, but we are not allowed to repeat the edge. So let us draw a trail. So suppose I move from A to B, right, and suppose I move from so B vertex has been B to F, and then F to E, and then E to B, and then B to C. So did you notice one thing? I started at B, I went up to from A I went to B, so the V vertex has already been covered. Then I moved to F, and then E, and then B. So we moved to the vertex B 2 times. We moved to 2 times because once I moved from A to B, so I just went there, and then again I moved to this, and finally I reached to C. So in this case the vertex B has been repeated twice. So this is an example of a trail where a particular vertex has been repeated more than once. Okay, and now let us understand that what is a path. So in this terminology, when we talk about a path, we are not allowed to either repeat the vertex or edge. So suppose I move from A to B, then B to C, then C to D, and then D back to E. So I started A to B, then B to C, C to D, and D to E. So this is a path because neither a vertex nor an edge has been repeated, right? I hope it is clear to you. Okay. Now the circuit is same thing. Circuit is a closed trail because in the circuit you know that a particular vertex, the initial and the final vertex are repeated. So suppose I move from suppose I take this example that I start from E, go to F, and then F to B, and then B to E. So here the vertex E where I started, I went back to the same vertex. So means this vertex has been repeated. So circuit is a basically trail, which is a closed trail. So this terminology I hope is clear to you. If I consider it like this, that the WAC is the most general term, right? WAC is the most general term. Then we have trail. So in trail we have only those sequence of vertices and edges in which the vertices may be repeated. The vertices may be repeated, right, but edges are not repeated, right? And we have talked about path. So path is the kind of most restricted thing where neither the edges nor the vertices are repeated. So from this figure you can see that all the path are trail and WAC also. Means this is kind of, WAC is a general term, on that we put the restriction that okay, you are not allowed to move from you are not allowed to travel one edge more than once, then it is trail. And if I further put the restriction that you are not even allowed to repeat the vertices, then you call it a path. So there may be some confusion among the student related to this terminology. I hope you are clear, because when we use this terminology we should stick to this. But I will be using the previous terminology where I will be just using the term path and simple path. And when I'm using the term path and simple path, basically we are not putting any restriction on whether a vertex is being repeated or not. If edges are repeated, then we call it a path. If edges are not repeated, then we call it a simple path. Okay. Now let us talk about connectedness in undirected graph. So what is connectedness in undirected graph? Just look at this thing that quickly, and then we will explain it through example. An undirected graph is called connected if there is a path between every pair of distinct vertices of the graph. An undirected graph that is not connected is called disconnected. We say that we disconnect a graph when we remove vertices or edges or both to produce a disconnected graph, disconnected subgraph. So let us talk about this through this example. Now if you look at this image here, the first graph, if you take any vertex here, you can move to any other vertex. Means suppose I take A and I want to move to G, so I can move to A to C, then C to D, and then D to F, and then F to G. Similarly, if I take E and I want to move to F, so I can move from E to D and D to F. You can take any two vertex and you can move from one vertex to the other vertex for any two vertices in this graph, right? So this is the example of a connected graph. This is the example of a connected graph. I hope you understand. It is a very basic term. I don't think we need to spend more time on this. But if you look at this graph, this is not a connected graph, because if I hope you understand that all these 6 vertices are the part of the same graph. So if I have to move from A to E, there is no path from A to E. How can I move from E to E? I can move from A to E. I can move from A to B. I can move from A to C. But I can't move from A to E. So this is a disconnected graph, right? This is disconnected graph. That is what the definition is saying, that the graph is disconnected. Okay. So this graph is a disconnected graph. Disconnected graph. Okay. Now you see that here in this graph there are three connected components. So this whole graph which is having the vertices A, B, C, D, E, F, G and H, this is the part of the same graph, but in this actually we have three components which are connected among themselves. So this is the first connected component of the graph, this is the second connected component of the graph, and this is the third connected component of the graph. Yes. Now let me take an example and explain to you a very important idea. Suppose we have a graph, right, gentlemen, and suppose we join it like this. Understand it very carefully. And when we join a graph, suppose we have a graph like this, let me name the vertices A, B, C, D, E, F. So if I remove an edge of the vertex, right, so I can simply remove an edge. This edge has been removed, and now you notice that the graph has become disconnected. Why it has become disconnected? Because this is one component which has 5 vertices, and we have just one vertex which is not connected to any other vertex, right? So when we remove an edge, we can simply remove an edge. But there is a problem here that if we remove a vertex, suppose someone says to you that remove this vertex C, right? So when you remove this vertex C, you have to remove all the edges which are incident on C. Let me repeat this thing. What I am saying, this was our graph originally. I hope this is what I have drawn. And in this graph, suppose someone says that remove the or delete the vertex C, right? So if I have to delete the vertex C, it means what? That I don't only have to delete the vertex C, I also have to delete all the edges which are incident on C, right? So by removing either an edge or a vertex, the graph can be made disconnected. Originally the graph that I have drawn earlier, means let me redraw it again. So this is the graph that I have taken, and this is a connected graph right now. Okay, you can see that you can have between any two vertices there is a path. Suppose you take B to F, then you can move from B to C and C to F. If you take B to E, means you can verify it that for any two vertices there is a path. So what is the point I want to repeat? The point that I want to repeat, that when I remove an edge, we simply remove the edge from there. Suppose I have to remove the edge between C and F, so I just removed this edge. By removing this edge, we noticed that the graph is still connected. Yes or no? But when we remove the vertex, then we don't only have to remove that vertex, we also have to remove all the edges which are incident on that vertex. So for example, suppose I have to remove the vertex E, so I will remove the vertex E, and along with that I will also remove those edges which are incident on E. So I hope you are clear about what do I mean by removing a vertex and removing an edge. So if you have understood this, let us talk about the next thing. Before I talk about this term, cut vertices and cut edge, I think you already have noted one important thing, that there is a simple path between every pair of distinct vertices of a connected undirected graph. So you can see that if you take any pair of vertex here, there will always exist a simple path between any two pair of vertices. Okay. Now what is the cut vertex? And that is also known as articulation point. So first let us look at the definition and then I will take the example. Sometimes the removal of a vertex and all edges incident with it. I repeat it. When I remove a vertex, we don't only remove a vertex, we also remove all the edges which are incident on that vertex, produces a subgraph with more connected component than in the original graph, right? I hope you are clear about connected component, right? That it may have more than one component, so the graph itself becomes disconnected, but it may have different connected component. Such vertices are called cut vertices or articulation point. And same thing, cut edge. What is cut edge or bridge? an edge whose removal produces a graph with more connected component in the original graph, a more connected component than in the original graph, I think there should be than in the original graph, is called a cut edge or bridge. So let us understand it through some examples. So let us take this example. So in this graph, we want to find the cut vertices and cut edges. For our convenience, we have drawn the same graph below here. So first let us find all the vertices which are cut vertices, right? Cut vertices. So if I remove a vertex A, it means what? That I need to remove the vertex, and along with that I need to remove all the edges which are incident on that vertex. So if you remove A, you notice that the graph that we are getting is still a connected graph. So it means what? That A is not a cut vertex. Okay, so A is not a cut vertex. Let me draw A and this edge. Now what is the next vertex that I want to remove, right? So let me remove the vertex B. So if I remove the vertex B, what will happen? We don't only have to remove the vertex B, we also have to remove all the edges which are incident on B, right? So B is removed. Now you notice that this becomes a disconnected graph. Why it became a disconnected graph? Because now it has two components. One component has the vertex A and another component is this component. So the example, this B is a cut vertex, so I write the vertex B here, and let me join this again so that we can proceed with the other vertices. Now if I talk about the vertex C, we notice that C, if I remove C, so the vertex C will be removed and all the edges which are incident on C will also be removed. So now this graph also became disconnected. So clearly the vertex C will also be a cut vertex. So I just take the vertex B here, I take the vertex C here. So C vertex is also a cut vertex. What about the D vertex? Sorry, D. So if I remove D, you can clearly see that removal of D actually is not creating any problem. The graph is still a connected graph. So D is not a cut vertex, right? D is not a cut vertex. I hope you are getting the explanation here. Up to now, I hope you have no doubt. So let me draw the D. Now what about E? I am looking at them one by one. So if I take E, if I remove E, clearly you can see that all these edges will also be removed and this graph again becomes a disconnected graph. So E is also a cut vertex. So I am going to write E also as a cut vertex, right? And let me join it again for our understanding. Now what about the other vertices? I guess that you are clear that removal of F will not make the graph disconnected, because this edge and this edge will be also removed. So an F vertex will be removed. See, this is also there. Similarly, removal of G will also not create a problem. I can show you. Suppose I want to remove G, then what I have to do? I have to remove G, I have to remove all the edges which are incident on G. So the graph is still connected. Similarly, H removal will also not make the graph disconnected. It means that only three vertices are cut vertices in this case, and those we already have written, that is B, C and E. Now what are the cut edges? So if I talk about the cut edges, let us remove them one by one. So if I remove AB, then clearly this graph becomes disconnected. So AB is a cut edge. So the edge AB is a cut edge, and this is how you represent the edge AB because you know it is an undirected graph. So you write the edge as a curly bracket. Now let me first rejoin it. And what about the BC edge? So if I remove the BC edge, the graph is still connected. So BC is not a cut edge, right? So BC is not a cut edge, or BC is not a bridge. If I remove this BD, then also the graph is connected. So BD is also not a cut edge. What about CD? So if I remove CD, this graph still remains connected. So CD is also not a cut edge, right? What about this edge CE? So if I remove CE, clearly you can see that the graph becomes disconnected. So CE is a cut edge. So let me write CE here, and let us proceed to the other edges. So now if I this was the vertex G. If I proceed with the other edges, I can clearly see, and now I'm not going to remove them one by one, because if I remove FE, then it will remain connected. If I remove EH, or let me show you so that at least you one problem should be clear to you. So if I remove this, it is still connected. So this is not a cut edge. If I remove this edge here, again it is connected. So this is also not a problem. And since it is a part of triangle, so clearly if you see that if you remove other edges, the graph will remain connected only. So there are two cut edges here, that is AB and CE. I hope you have got your idea clear. So let us move to a next problem, and pause the video and try to answer it yourself, that which of the vertices or edges are cut vertices or cut edges in this case. Okay, so pause the video and answer, and then proceed with it, so that you can compare your answer, that whether it is right or wrong. So let me quickly talk about this. So here I am going to write the answer directly. So if I remove A, then the graph will remain connected. If I remove B, because this is the part of a triangle, you can clearly see that removal of A, B and C will not create a problem. If I remove D, is still connected, E is still connected, F is still connected. But if I remove C, then it will become disconnected, because if I remove C, I will get the graph like this, that I will get A here, I will get B here, I will get D, E and F. The C has been removed, so I will get something like this. A, between A and B, the edges will be there, and this edge, this edge, this edge and this edge, because there are 4 edges incident on it, so it will be removed and I will be getting this graph. So C is a cut vertex. So for this example, one of the cut vertex is C, right? What about the cut edges? So clearly you see that if you have this graph here, I am going to draw this again. If I have this graph here, clearly removal of AB will not make the graph disconnected. Removal of BC will also not make the graph disconnected. Removal of AC will also not make the graph disconnected. Same is true with CD, same is true with CF, right, and CE and ED. So in this graph, basically there is no let me write it, no cut edge is available, right? So I hope you have understood the idea of cut vertex and cut edge. I would suggest you to solve this problem, and I think for you I also have another problem here, or can I do this problem for you, that which of the vertices are cut vertices or cut edges, and this time I'll be very quick, so that you understand it. You already have understood it. So what are the cut vertices? Removal of A, so will not create any problem. Removal of A, the graph will still be connected. B will be a cut vertex, because if I remove B, then I will be having a vertex A which will be isolated. So B will be a cut vertex, right? What about C? So if I remove C, then I will get the component AB. So C will also be a cut vertex. E, D will not be a cut vertex. E will be a cut vertex, because all the edges, these 4 edges will be removed. So E will be a cut vertex. And what about I? So if I remove I, then I will also be a cut vertex, because I will get this isolated vertex H here. So I will be a cut vertex. G will not be a cut vertex, F will not be a cut vertex, H will not be a cut vertex. So the cut vertices are B, C, E and I. And what are the cut edges? Cut edges, can you answer it? So AB is a cut edge. Yes, let me first remove all those lines here, and then I will answer it. So let us be clear. So AB is a cut edge. Yes, AB is a cut edge. So I'm writing, because if I remove AB, the graph will become disconnected. What about BC? So BC will also be a cut edge, because if you remove BC, you will have this component and another component here. So BC will be a cut edge. What about CD? So CD will also be a cut edge, because if you remove the edge CD, the vertex D will become disconnected. What about CE? CE is obviously cut edge, because you will get two different component. What about EI? So EI will also be a cut edge, because if you remove EI, it will become disconnected. IH, so IH will also be a cut edge, because if I remove IH, H will become disconnected. Now EF will not be a cut edge, EG will not be a cut edge, and FG will not be a cut edge. So the cut vertices are BC, EI, and the cut edges are AB, BC, CD, CE, and EI and IH. 1, 2, 3, 4, 5, 6. So there are 6 cut edges and 4 cut vertices. I hope up to this idea is clear. Now finally, we are done with cut vertices and cut edges. Now let us talk about connectedness in directed graph. So when I talk about connectedness in directed graph, before that we have a remark also, that connected graph without cut vertices are called non-separable graph. So this kind of question may be asked, that if in the graph there is no cut vertex available, then we will call that graph as a non-separable graph, and can be thought of as more connected than those with a cut vertex. Means we can consider it that there is a strong bond between the vertices, because removing any of the vertices is not leaving the graph disconnected. So those kind of graphs are said to be non-separable graph. So what is the definition of a non-separable graph? A graph is said to be non-separable if it does not have any cut vertex. Now what is connectedness in a directed graph? A directed graph is said to be strongly connected if there is a path from A to B and from B to A whenever A and B are vertices in the graph. And when it is weakly connected, a directed graph is weakly connected if there is a path between every two vertices in the underlying undirected graph. Means what does that mean? Let me repeat it. A directed graph is weakly connected if there is a path between every two vertices in the underlying undirected graph. To understand this, let us take this example. So if you look at this example here, here in this example you take any two vertex. So between any two vertex there is a path. Suppose I take the vertex A and D, right? So you can move from A to B and then B to D. Suppose you take E and B, so you can move from E to A and A to B. You take anything, like if you take C to A, so from C you can move to D, D to E, E to A. So, and I hope you understand that here the movement is allowed only in the direction where arrow is pointed. You can't move from B to A, right? You can't move directly from B to A, but certainly there is a path from B to A, because I can move from B to D, D to E, and then E to A. So this is an example of a strongly connected graph. Why it is strongly connected? Because between any two vertices, and that is true for every pair. I'm not saying just A or D or B, C or D. You take any two vertex, and between any two vertex there will be a path, right? There will be a path from between any two vertices. Then this is said to be a strongly connected graph. So look at the definition again. A directed graph is strongly connected if there is a path from A to B and from B to A as well between any two vertices in the graph. So here you can see that if I'm taking A to D, A and D, so there is a path from A to D, and there is also a path from D to A. Same is true for any two other vertices also. So this kind of graph is known as strongly connected. But if you look at this graph, suppose if you remove the arrows, then the graph that we say get is said to be underlying undirected graph, right? Underlying undirected graph. If you just remove all the arrows here, so in this graph you can say that you can see clearly that you can move from B to A. So there is an edge between B to A, but here you can't move from A to B. There is no path from A to B. Can you move from A to B? No, you can't move from A to B. Even though if you remove all the arrows, here, the graph that you will be getting is an undirected graph, which is a connected graph. But if you look at the directed graph here, between A to B there is no edge. You can't move from A to B. So because for these two vertices there is no path from A to B, this graph is said to be a weakly connected graph. Okay. So we just understood the concept of a strongly connected and weakly connected in case of a directed graph. Now the last thing that we are going to talk about is paths and isomorphism. So we know that there are several ways that paths and circuit can help us determine whether two graphs are isomorphic. For example, the existence of a simple circuit of a particular length is a useful invariant that can be used to show that two graphs are not isomorphic. What does this mean? In case if you didn't get it, let me explain it through this example. Suppose they ask this question that what about these two graphs, are they isomorphic? So when I look at the second graph here, we can clearly see that we have a simple circuit of length 3. You can see that I move from U1 to U2, sorry, this is V1, so V1 to V2, V2 to V6 and then back to V1. So we have a simple circuit of length 3 that is present here. But in this graph we don't have a simple circuit of length 3 present. So just by this characteristic which is not being shared by both this graph, I can conclude that the graph G and the graph H are not isomorphic. Okay. Now let us look at this graph, and here I will give you the hint. I am not going to solve the complete problem, but I hope you will be able to complete that. So the hint that I am going to provide you, that what do you think whether these two graphs are isomorphic or not? Pause the video, first decide and then play it. So first of all, you can check other characteristic like number of vertices, number of edges, degree sequence, and since I have talked about graph isomorphism in detail in our previous video, I hope you might be aware about these terms which I have used. Now whether this graph will be isomorphic or not, for that you have to define a 1-1 onto mapping between the set of vertices here in this graph G and the set of vertices here in this graph H. But just to give you a hint, I am going to look at a different picture. The picture here is that if you look at this graph here, you have a cycle or simple circuit of length 3. So you can move from U1 to U4 and then U4 to U3 and then U3 to U1, right? And here also you have a simple circuit of length 3. You can move from V1 to V3, then back to then V2 to V1. So both simple circuit of length 3 are present, right? So this is one property that they are sharing. Now let us look for another thing, that whether we have a circuit of length 4. So in this we have a circuit of length 4, 1 2 3 4, and here also we think we have a circuit of length 4. Can we find out? So suppose I move from U1 to U5, right, then U5 to U2, then U2 to U3 3, then U3 to U4 4, and then this is 5. So basically we are getting a circuit of length 5, and here also we have a circuit of length 5. You can see that I can just move from V1 to V2 to V3 to V4 to V5, and we have a circuit of length 5. But actually I was looking for a circuit of length 3. So let us, sorry, length 3 we already have seen. I was looking for a circuit of length 4. So before I find out, let me again repeat. Here we have a circuit of length 3 in both the graphs. We have noticed that we have a circuit of length 5 in both the graphs. We have noticed that we have a circuit of length 4 in the second graph, and I just want to find a circuit of length 4 in this graph. So can you help me to find the circuit of length 4 in this graph? So yes, here is the circuit of length 4. Suppose I move from this vertex U1 to U5, then U5 to U2, then U2 to U3, U2 to U3, and U3 to U1. I repeat it, U1 to U5 length 1, then U5 to U2 length 2, then U2 to U3 length 3, and then U3 to U1 length 4. So here also we have a circuit of length 4, and in the other graph also we have a circuit of length 4. So we have noticed we have a circuit of length 3 in both the graphs, we have a circuit of length 4 in both the graphs, we have a circuit of length 5 in both the graphs. Now I would leave this problem for you to decide that what will be 1-1 onto mapping between these two set of vertices, and after that you need to write the adjacency matrix to prove that these two graphs are isomorphic. And since you have sufficient hint that the circuits are there, so you can try to match the vertices between these two sets of graph. So I hope you will be able to do it, and what I would suggest you that define the mapping and put that mapping in the comment section, right? So that I can guess that whether you have done it right or not. Once you will be able to define the mapping, the adjacency matrix part is of course very obvious. Okay, so I discussed lot of different things in this video. I discussed about connectivity, and I talked about two terms, path and simple path, and in another set of terminology they use walk, trail and path. We talk about cut set and cut vertices, and then we talked about path and isomorphism. So that is all for the video. In case if you liked the video, please press the like button and share it with all your friends so that they also get benefited from this. Thanks for watching.